Alrighty, cool. Welcome to lecture 3 of the math class. The bulk of it will be multiplication, but first we'll do a little review. So first, numbers. So before, I talked about, like the notion of 3. I think of this as 3, and I kind of think of this as 3, and I kind of like, oh, well, they're the same because I can map them together, right? That works for humans. Humans are good with just extrapolating. But in mathematics, we like specific kind of something to work with. Just kind of saying, well, that's that. I think of those things as 3 and that thing as 4. A little hard. So here's what numbers mean in mathematics. At least one version. So the one notion we need is that of some kind of container. So we'll just call this a container. Math calls it a set, but whatever. Just something you can put stuff in. So what's the first number?
1.
Yes, often. But what's the other first number?
0.
0. And what does 0 represent?
Nothingness.
Right. So with the concept of a container, an empty container equals 0. Empty container. So that's what 0 is. 0 is nothing. Seems nice. What is 1? 1's got one thing in it. What do we have so far? What's one thing that we have?
One item in the container.
Right. What item do we have?
An elephant.
No.
Oh.
That's reality. We're working in the void where nothing exists.
A 0?
Yes. So 1 represents the thing with 0 in it. All right. What about 2? What do we throw in 2? What does 2 mean? Well, we've got 1, and we need something else too, right? 0. So we throw in 2 things. 0, 1. That's all we got. That's all we need. And then we proceed. So 3 is a thing with 0, 1, 2. And 4 is the thing with 1, 2, 3. Or 0, 1, 2, 3. And so forth. So that is a way of making an infinite set of numbers out of nothing. Thank you very much. Now, what would addition be? For this, I need colors. So, 2 plus 3. Well, 2 is, oh, actually, I don't want to. 2 plus 3. Let's make it Christmas time. We got gifts. We got 2 gifts and 3 gifts. How many gifts do we have? We've got 5, certainly. How does it work out here? Well, what is 2? 2 is 0, 1, right? Oop. 2 was green. So this is 0. Think of that as 0, 1, and 3 as 0, 1, 2. And so if I want to combine them, what would I do? If I wanted to make one big container with stuff, throw it all in there, right? So let me go with blue. Let me not go with blue. That was supposed to be a good marker. All right, let me go with purple. Okay, purple's mean. So I have a big container. I throw in 2, 0, 1. I throw in 3, 0, 1, 2. I've made them different colors so that we now have 5 things. And then we just kind of relabel. And we just kind of like think of this 0 as, well, no, see, I need purple. Purple. So can do a 0 for the 0, 1 for the 1, and the red 0, that'll be 2. So I just kind of map that to a 2, and then the red 1 to a 3, the red 2 to a 4, So 0, 1, 2, 3, 4, and that is 5. So that is how mathematicians think. Be careful talking to mathematicians. Phil?
Why are you starting with 0?
Because it's nothing.
Why not start with -1?
Because 0 represents nothing. I can start with nothing.
But why do we care to, why are we doing this representational thing? Like, it's going to be easier to follow if we start with 1, right?
What do you mean?
2 is a box with 1 and 2 in it. 3 is a box with 1, 2, and 3 in it, rather than 3 is a box with 0, 1, and 2 in it.
Well, I'm trying to define what 2 is, right? I can't use 2 in defining 2. This,
How does that actually define 2?
what do you mean? 2 is this container with 0 and 1. I've defined 0 and 1.
Okay. This isn't some abstract, like, we're just doing this for now, or is this how we should think of the number 2 at all times?
No, you should not. You should think of 2 as however you like to think of 2 as being 2 things. I do actually have a use for this later on.
Okay.
But it's mostly just it's a way of saying that this is what this thing actually is, rather than just kind of a hand wavy, like I know what 3 is. So we all know what 3 is, but you know, it's actually like this is something you could theoretically kind of make a computer deal with. It's, you know, hard to make a computer deal with like recognizing necessarily what 3 is on its own, but you could say that, and then you have things that represent. I mean, it's starting from nothing. It's just the main point.
Okay.
Alrighty. Okay, so that's numbers. Now, right. Now we'll do a quick review of the addition subtraction methods that I introduced before. I guess I did both addition and subtraction last time. Now, one thing that's, you know, kind of a thing you need to do is, you probably already have it, but memorize the sums of, single digits summing up to 10. So everything I do, that's sort of a important sort of thing in the mind to have. So something like, if I were to write this, instantly in your head, you should just think 7. Don't read it as 3 plus 4. Just look at it and say 7. Okay? That's the kind of thing I'm talking about. Now, there's a particular thing that we use over and over again to make things easier. It's called complements, and it's these things that are add to 10. So 9 and 1, 8 and 2, 3 and 7, 4 and 6, and 5 and 5. These are the things. You see 9, you should think of its partner as 1. You see 8, you should think 2. These are the things that sum to 10. All right. Okay. So that's complements. Now, and we use them in addition. So, like, if you do 5 plus 7 plus 8 plus 3, doing this. All right, 5 and 7. That's going to be something larger than 10. So the complement of 7 is 3. So we need 3. We get 3 from 5, and that leaves a 2. And so I've got 2 in my mind, and I've now got an extra kind of 10 here. So kind of, this was 12, but in my mind I'm thinking 2, and on my finger I've got the 1 for the number of 10s. And then the 2 and the 8, That becomes a 0, and another 1 here. So that 20 basically in the head, but think 0 and have on your hand the 2. And then with a 3, add it to 0, you get a 3. So it's 23. That was the basic thing of addition. When doing a big sum of numbers like that, counting on your fingers for the tens is useful. But if you're just doing like a sum of 2 numbers with multiple digits, that's a little less important. 5, 6, 7 plus 3, 4, 8, for example. Do I start on the left or the right? Left. So over here. That's an important thing to always keep in mind for all operations. Start on the left. That's what matters. That's what's useful. So 5 and 3, that's 8. And then 6 and 4, that's a 0 with a 1 that carries over. And for this, underlining this digit is convenient. And then 7 and 8, that's a 5 with an underline here. And the underline means you add 1. So 915. Okay. Questions about that technique? Now, with subtraction, let's subtract these two numbers. 567 minus 348. All right. Again, we're going to start on the left. 5 minus 3, well, that's a 2. 6 minus 4, that's a 2. 7 minus 8, that's a negative number. So that's where we use that complement. We replace this 8 with 2 and add it to the 7. And then we slash the number to the left, indicating that we needed a 10. And we get 219. Okay. Let me try another one with another extra complication. Again, from the left, 5 minus 3 is 2. 6 minus 6 is 0. 7, 8. So again, flip the 8 to a 2, add it to the 7. That's a 9. So you slash it. Now, I slash to 0, which means I'm making that into a minus 1. That's a problem. So I slash the 2 on the other side of it. And now I've got 1. The 0 becomes a 9. And 9. 199. Alrighty. Now, one can ask what this flipping the 8 with the 2 is all about, why that works. So let's try a little example that I do it in a couple of ways. So 43 minus 28. With this method, I would do 4 minus 2 to get 2. 3 minus 8, 8's too big, replace it with a plus 2. So 2 plus 3 is 5, and I've slashed it when I did that complement, so it's 15. Now, expanding this out, kind of horizontally, 43 minus 28, I can write this as 40 plus 3 minus 20 minus 8. Everybody good with what I'm doing here? So 43 means I've got 4 10s, that's this 40. I've got 3 1s. 28 means I've got 2 10s, 20, and 8 1s. And I want to subtract both the 20 and the 8 because I'm taking away a total of 28. All right, so if I was doing this without thinking about this method, I would just do 40 minus 20, 3 minus 8, which is minus 5, and then I'd get a 15. Now that having this thing be a minus 5 doesn't work with that method, and so where the complements come from is a trick which is one of the fundamental tricks in all mathematics. I do nothing. I love that trick. So 40 plus 3 minus 20 minus 8, I add 10 and I subtract 10. Adding 10 and subtracting 10, am I doing anything? No. So it's adding 0 to this thing. It's doing nothing. I'm doing nothing. Fine, stupid. Why am I doing this? Well, I'll tell you why I'm doing this. I'm going to rearrange this thing. Well, first of all, I'm going to put the 10, 40, and the 20 over here, plus 3, and then I'm going to move that 10 over here, and the minus 8. I've got this minus 10 somewhere here. 10 minus 8 is what? 2. The complement of 8, 2. So 40 minus 20 plus 3 plus 2. And I got this minus 10. So I've got my 5, and I've got my 20. They're all being added, and then I've got this extra 10. So this 10, that's the slash. That's what I'm slashing. So I'm moving this minus 10 over to this 20. So it's 20 minus 10 plus 5, 10 plus 5, 15. So the replacing the 8 with a 2 and adding, that's, I'm taking this plus 10 that I threw in there. 10 minus 8 is plus 2, got a 5, I'm good there. And then I do a slash, because when I added this 10, I had to subtract 10. And there you go. So by doing nothing, I made the problem easier to do. You don't need to understand that to know the technique, but it is helpful in the pursuit of getting to algebra, because we do that kind of trick all the time. Adding 0. It's an inspirational trick. It's magic almost. It's also doing nothing. All right. Any questions about all that? So much for addition and subtraction. Now we get to multiplication. Now, addition is probably the most frequent operation one does in arithmetic, but multiplication, this is the pure power of math right here. This is where you need to know multiplication in order to be able to use math in like wizard type level stuff. Like, this is the thing. And just like the addition and subtraction, I'm going to teach a method that is not generally taught, because that's who I am. All right, but first one has to start with the single digit multiplication. Digit multiplication. So something like knowing 5 times 9. So to really be able to do multiplication, you need to be able to look at this and instantly say 45. This is not something that you want to compute out every time you see that. It's something that needs to be internalized. It's memorization. Now, there are a few ways of memorizing things. You can make multiplication tables. It's a very common one. So one column going down, well, I don't know if you need 0, but 1 through 9, 1 through 9, and you do this you fill in all the different multiplication stuff. You get a nice grid. You know, you play around with that. You stare at it. You memorize it. You get a feel for it. You see patterns. You do whatever you want with it. Plenty of those exist and around. Another option is to actually compute it out a few times. So 5 times 9, what does fundamentally multiplication mean? Repeated addition. So I'm saying here, add 9 with itself 5 times. So making that claim. So that's what that stands for. So you do 9 and 9 and 9 and 9 and 9. All right, and then you just add it. We know how to add. So 9 and 9, well, that's going to be more than 10. Complement of 9 is 1. So 9 plus 1, so I got a 1, and I'm left with an 8. And then I do that again, so I get 2, and then there's a 7. Do it again, 3 and a 6. Do it again, 4 and a 5. So, quick way of adding them all up together like that. You can also, if you're crazy.
Emergency art court meeting in the art room. Emergency art court meeting in the art room. Thank you.
Okay. You can also like get a lot of pennies and start counting them out. I don't recommend that, but that would probably be a strong motivator to memorize these things. There's also, for something like 7 times 8, there is another technique, which I intend to do later when I've got a little bit more tools to work with. But as long as you know that that's 56, that's all I care about. But I'll give you something to help you figure that out. All right, but single digit multiplication, there isn't much I can do to help you with it other than just say you got to know it. So 3 times 7, 21. And again, like when you're staring at these things, don't say 3 times 7 to yourself. Say 21. And this is a word. Don't read the letters. Just say the answer. 3 times 7, don't say. Look at it. 21. 45. 12. Okay. Just like that. All right. Now, let's see. What do I want to do? All right. Before I quite get to the too much into the multiple digits, another thing with single digits and also other forms of multiplication is the idea of a box. So let's say I want to do 4 times 3, this 12 thing. So one way of doing it, is to think of it as a box. One side has it's going to have 4 areas, 3 lines. Going down, 4 columns, and the 3 is going to be represented by rows, and then you just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, and you know you can do the same thing on this floor here. 4 times 3. There's a certain sense of reality to multiplication when you kind of view it as this box style. Now, if I wanted to do something like 2 plus 2 times 3, so one way is, of course, I can view that as 4, and 4 times 3. But another way of doing it is also kind of thinking of it as 2 times 3 plus 2 times 3. I've kind of distributed the 3. This is the distributive property of multiplication, and I can tell you that about like 80% of everyone's math phobia in algebra, calculus, whatever, comes from something relating to this property. The distributive rule is something that seems nice and easy, hopefully, particularly after I explain it a little bit more. But when you start having letters and algebra and stuff, all sorts of crazy stuff happens. And later on you have things that look like that but aren't. So it's important to have a kind of a clear head about this. Now in terms of these boxes, I can kind of think of doing these things here. So the 2 plus 2 part would be just kind of considering this as having 4 all the way across. The 2 times 3 would be counting this. And then this 2 times 3 would be counting this. So kind of visually with the boxes, that's kind of how it looks. I mean, kind of a bit more is you kind of have two separate boxes, and you kind of join them at the purple line, and then you get the 4. So that's sort of the distributive property. You can either do your addition first and then do the multiplication, or you can distribute the thing outside in, do the multiplications, and then do the addition. All right. Now on to multiple digits. Let's start fairly small. 23 times, 2. All right. Somehow I feel like I should put an X there. Training. X's are bad. Don't use X's. All right. So, what is this? 23 times 2. How am I going to proceed? Right?
The answer is 46.
Mm-hmm.
Should I explain how or just 46?
Would you like to?
Not really, I guess.
Oh, okay. So, to start slowly, we can, of course, view it as addition. And we got a 4 here and a 6 here, and that's 46. So that is the answer using our previous tools. But the technique here is, again, this is different than conventional. I want to start on the left. Start on the left. 2 times 2 is what? 4. And 2 times 3? 6. So that's 46. And it's that simple. For multiplying by a single digit, and I don't have any kind of weird carry stuff. And what am I kind of doing here? I'm kind of doing 20 times 2 plus 3 times 2. So in this kind of methodology, I'm kind of using this. I'm breaking it up. I'm doing the 2 tens times 2, that's a 40, and the 2 3s here, you get 46, and then that's just 46. Okay? So this is the fundamental truth of why this works, but operationally, you take this number, multiply it by this, write it down here, multiply this number by this, write it down here. Now, I did an example that didn't have a complication. Now let's do one with a complication. Alrighty. Let's say 29 times 2. All right. I'm going to start the same way. 2 times 2, 40. But now I come over here. 2 times 9. What is that? 18. I can't write 18 down here. That would make it look like it's 418, which it definitely is not. Also, I should probably emphasize it's always good to round when doing a problem. It's not really necessary for this, but 30 times 29 is kind of like 30. 30 times 2, the 3 and the 2 is 60. Should be around 60. Definitely shouldn't be like 420. So, what do I do? Well, so 2 times 9, as I said, it was 18. So I write a 1 down here and an 8. And I can add them up and get 58. I can also, if I choose, think of it as with our little underline notation. I got 4. I say 18. Okay, there's a 1. I'll put that there. And then do that. And then I know the underline. I should add the 1. So either way is fine. And as we move on, I'll try to suggest to kind of do this step in your head, but take it slow. Now, let's see. In terms of doing it out like that, and so it's 20 times 2 plus 9 times 2. I've got the 40 and I've got the 18. And so what I'm doing here is I'm breaking that 18 up into 10 and 8, combining these things, and I get myself 58. So this is kind of the truth of the matter, and this is the convenient form to actually write it out. Okay, any questions about that? Okay. Let's do something else. I don't know. Let's say 863 times 5. So, I don't know. In my mind, just real quick, I'm thinking 800 times 5, 4,000. So that's good. Now, again, going from left to right, 5 times 8, I just kind of almost said it, it's 40. So I'll write down 40. And then 5 times 6, that's 30. So I'll write a 3 down here, put a 0 here. And then 5 times 3, 15. Put a 1 there, put a 5 there. And then I sum them. 4, 3, 1, 5. Easy peasy. Now, let me write this in red for bad. Here's the traditional method. So what they would have you do, and it's not terrible with just one digit down here, they would say 5 times 3 is 5, put up a 1, 5 times 6 is 30 plus the 1. So you got a 1, you carry a 3, 5 times 8, 40 plus 3, 43. So the traditional is starting on the right, you write some numbers up here, you do some multiplication and summing like that, and it's okay with that. But again, it's going the wrong order. The 4,000 here is what matters the most, so try to get that right. This technique also has the advantage that if you want to stop at some point, like if I only did kind of like this much, I'd have an estimate of 4,300. If I start with the traditional method and I stop after 2 steps, I've got an estimate of 15. It's totally garbage. So you're actually, the computations you do here are self-estimating. Here, estimation is a totally separate kind of ball of wax. How many digits are in this number? 4. How many digits are involved in this multiplication?
3.
Well, 3 in the first one, and then a fourth one here, right? So, yeah, still got this. Number of digits in answer equals number of digits in multipliers. Okay? So if you want to know how many digits you should have at the end, you count them 1, 2, 3, 4, and you should know it's 4, so you're thinking the thousands. Now, what I've just said is false, unless I've thrown a caveat. And the reason it's false is actually on the board. I have 29 times 2. How many digits? 1, 2, 3. How many digits? 2. So this has the caveat of 2 times 2 is 4, right? 4 is also 0, 4. So this applies if you always think in terms of your multiplications as having 2 digits when you're done, even if there's only one non-zero. So this is kind of this phantasm 0. May have one leading 0. So when I count these things, like I know it's 4, and maybe it's 3 if I don't actually, if I have 2 very small multiplying things here, and I don't have to carry. But otherwise, it's a good kind of thing to have in your mind, just how many digits you might have. 4, 3. Gives you an estimate kind of immediately. Alrighty. Now this, whether you go left to right or right to left, I don't think it makes that big a difference for the single digits you're multiplying with. But I think it does actually make a difference when you're doing it with larger things. So, I don't know. Let's say 429 times 45. All right, actually, let me just stick with, just do 49 times 45 to start off with. 2 digits times 2 digits. So how many digits should I have in the end? 4. Maybe 3, probably 4. And definitely 4 actually for this one. All right, so again, I start on the left. 4 times 4 is 16. 4 times 9 is 36. I stop. And now 5 times 4 is 20. So for this one, I'm kind of 1/10 place to the right, so I'm going to put that leading digit here, one to the right. So 5 times 4 is 20, and then 5 times 9 is 45. And now I add, again, starting from the left, I've got a 1. 6 and 3 is 9, 9 and 2, that's going to be greater than 10, so 9 plus 1 is the 10, so I've got, well, I'll just dash it under here, and I have 1 left over, kind of 11. 6 and 4 and 0 gives me a 10, which I write as a 0, underline here, and then I have a 5. So 2,205 should hopefully be the answer. So there you go. Yeah. And kind of just, if I was actually caring about this problem, I would initially look at it as sort of like 50 kind of times 40 and compare it to 50 times 50 50 times 40 is like 2,000. 50 times 50 is like 2,500. And it's going to be somewhere in the middle here. So maybe like 2,200, 2,300, something like that. That's often all you actually need, but this is how you do it out. So 2205 doesn't seem wrong to me. Could be wrong. Phil, is it wrong?
No, it's
Oh,
not.
nice.
I find this a bit wonky.
Wonky.
Yeah, because you're sort of extending, you're losing the significance of your tens places. You know, like your decimal places don't have any significance as you are solving the problem. So, for example, the 200, you know, the figure that comes out to be in the hundreds place, that lines up with your tens places at the top, rather than a hundreds place.
Well,
So you start writing 16 as that person's solution. Yeah, but
does that make you happy?
no, it doesn't, because the zeros are in the 0.1 decimal place.
0.1.
Yeah, if you're starting with 49 and 45, the stuff below the 9 and the 5 should be the ones place, but it's not. It's the tens place. The stuff below the 4 and the 4 should be the tens place, but it's the hundreds. Oh.
Does that make you happy?
Yeah, or so. But it involves, I don't know, it involves knowing like where to put stuff in a way that hasn't been explained. So.
4 digits, if you want to. I mean, I think ultimately it doesn't matter. You have your answer here, but 1, 2, 3, 4, 4 digits.
Well,
You
it does
start
matter.
4 digits
Midway
over.
through that problem, that last problem you said, like, and we know we need to put this in this lane, basically, because X, Y, Z, but you didn't
Oh.
follow that logic from the start.
What are you talking about? So you start here somewhere, wherever you want to put this number, and the next one, when you move over to this digit, you write that down 1 over to the right.
I get it, but it's all shifted.
And if you like grids, you can make it in a grid. You can do it properly that way. But it's, I don't know. I mean, really, the way, I mean, you can just not even write down the multiplication problem and just start writing down the number. You don't need it there in the first place. All right. Now, let's do it the traditional way, just so you can see and contrast. See if I can actually do it that way. So they would have you do 5 times 9 is 45, 5 and a 4, 5 times 4 is 20, plus 4, 245. Then they'd have you put a 0 here, and then 4 times 9, 6, 3, 4 times 4 is 16, plus 3, 1960. And you add from the right, because that's what they like. 1, 3, 10, no, 10, 2, 2, 1, 2. So, yeah. One thing to notice is we're kind of overloading the carrying numbers over here when you do it the traditional way. And again, you're sort of starting with the least significant stuff. And I don't know. I find this method fun. I find that method tedious, personally. Suit yourself. Alrighty. Let's try another one. Uh, 587 times, I don't know, 393 times that. All right, how many digits in my answer? 6. 6 digits. And what does that mean that what range of that is it? Like 1,000, 10,000, 100,000, million, 10 million? So if you've got 6 digits in a number, 3 and a 3. Yeah, so it's somewhere, between 1,000,000 and 100,000. If I lose a digit, like if this was a 1, then it would be in the tens of thousands. But all right. So if you want to properly line the grid up, you can start 6 digits over to the left. All right, 5 times 3, 15. 3 times 8, 2, 4. 3 times 7, 2, 1. Next number is 9 times 5, 45. 9 times 8, 72. 9 times 7, 63. 3 times 5 is 15. 3 times 8 is 24. 3 times 7, 21. Alrighty, let's see if I end up with 6 digits. So, 1, 5 and 7, and another add on the 4, so that becomes kind of 11. Put a dash under this. 4 and 2, 6. I have a 1 in my mind. 1 in my mind, and I'll put a slash here. 1 and 7, 8, and then 9. And then here, 1 and 2, 3, 6, 9, 5, 15. 3, 6. Well, that's 9. I take 1 away. Put down a 4 in my head. Put a slash here. Another 2. So that's 6. And then 3, 4, 7, 9, and 1. Wow, actually 6 digits. All right. And now the underlines mean 2, 2. Now I've got a 0. So if you're looking ahead, you could realize that. If you don't, that's fine. Just underline it again. So 230,691. It's not too bad.
Is it right?
Okay. Since the question was asked, well, actually, I don't want to do that at the end. There is a way to check whether it's right. Let me see in my head.
It's right.
All right.
You already did it in your head.
No, there is a trick to it. 3. What is this? 6, 9. Yeah. I'll show it to you. Don't worry. Oh, I may not show it to you today. Okay. So that's big number multiplication. I'm going to leave it this way, but I do want to mention, because it'll be useful when we deal with division, that, how I was writing this number here, like the 2, that was coming from 3 times 8, which is 24, that 2. The good technique for when you want to deal with division is you say, okay, 3 times 5, there's a leading 1, write down the 1. 3 times 5, there's the second digit is a 5. You keep your 5 in your mind. 3 times 8, the left digit is a 2. So 2 plus 5 is 7, and you'd write down the 7. And you don't have this little line here. And so instead of having 1, 2, 3, 4, what is that, 6 lines, you'd have 3 lines. So it's kind of like combining this 5 and the 2 in your head. So that would be just a 7, and that would be a 6. I think if anyone wants to practice this method, which I encourage you to do to master it, writing it out like this is a good starting place. And once you're comfortable with this, then start thinking about how you can do this kind of addition in your head. Again, I don't think it's a big deal when you're doing multiplication, but doing the division techniques, it is. Okay. So that's the nitty-gritty of multiplication. If you want to multiply more numbers, you multiply 2 numbers first, then you multiply the third and the fourth and stuff. I don't know of any great way to simplify that process any further. All right, now, minus 2 times 3. What is that? Right, so the answer is minus 6. What does it mean? So what did I say multiplication meant? It was repeated addition, right? So 2 times 3 meant 3 plus 3. So what does a minus 2 mean?
Negative 3 plus 3?
Well, so instead of repeated addition, kind of repeated subtraction. So
You gotta get more or less.
more or less.
More or less. More or less numbers.
Repeated subtraction. So you take, it's kind of a hanging subtraction, if you will. It's minus 3 and minus 3, kind of subtracting from 0, and you get minus 6. All right. Now, that's on the one side. What about 2 times minus 3? This is a little bit slightly different. So this is sort of minus 3 plus minus 3. And that's also kind of minus 6. So here, you know, there's this kind of 2 different sides of thinking about like this leading multiplier is sort of like how many times you want to do the addition, and then over here is what you're actually doing the adding of. All right. Okay. Now, another way of kind of thinking of this is apply a debt of 3 twice. So it's like I have some money, I'm removing, or I don't have money actually. I'm borrowing. I'm borrowing $3 twice, and so I borrowed $6. All right. Now, for the mystery. Minus 2 times minus 3. What should that be? Should be minus 6 plus 6, 27. I like 27. It's not 27.
I'm going to say minus 6.
Okay. Vote for minus 6. Any plus 6s? All right, I got some plus 6s. It's minus 6s. So how do we think about this? Traditional way is just say minus times a minus is a plus. So it's plus 6. But that's just telling you that's a rule. How do we think about this? Well, kind of repeatedly twice. Subtract a debt of 3. So if I'm subtracting a debt of 3 from my overall holdings, what does that mean? That means my debt is going down, right? And so that means kind of the money I have is going up. Equivalent to getting 2 plus 3 amounts. So if you think of, if I'm in debt $10 and somebody removes my debt of $3 of my debt once and then twice, now I'm only in debt $4. So that's why it's plus 6. All right. So one negative sign, you get a negative number. 2 negative signs, you get a positive number. And if you got 3 negative signs, well, you can follow that up by every 2 negative signs becomes a positive. So 3 negatives, you get a negative, so forth. All right, so that's negative multiplication. Okay. Any questions about that? All right. Now for kind of a question mark. 3 times 5, 5 times 3, are they the same? So I've described them as 2 separate things, right? This one kind of means 5 plus 5 plus 5. This one means 3 plus 3 plus 3 plus 3 plus 3. Hopefully. All right? This sums to 15. This sums to 15. So they appear to be the same, but I've described them in 2 very different ways. So, is it generally true that we can flip the 2 in multiplication? Yes. And let's see how this plays out. So, what was 5? 5 was 0, 1, 2, 3, 4, right? That was from the beginning. So these are kind of my elements of 5. I've got these 3 containers with 5 things in them. Now, I want to see how this, combining these 5 things, 5 in each of them, comes out to be the same as adding all these 3's together. So, actually, I guess I should have used a different color here. Okay. Anybody see what I might do? How do I see that I've got sums of 3's going on here? Well, I've got a 0 in each of these, right? So I can write 0, 0, and 0. I've got 3 things. And then I can do the same with 1's, and then 2's, and then the 3's and the 4's. I guess I'll just. I've got 5 of them. Oops. Okay. I've got 5 of them because I had 5 numbers in each of these things. And I've got the same thing repeated 3 times because I had 3 terms. And so I can relabel these things 0, 1, 2, or that's just 3. So it's 3 plus 3 plus 3 plus 3 plus 3. So it's like I have 3 groups of 5. I pull 1 from each of those 3 groups. And I make a new group. I do it again, make a second group, third group, fourth group, fifth group. And this is how I end up with seeing that the 3 5s and the 5 3s are the same. And this is called the commutative property of multiplication. Okay. Guess I kind of did that. All right. Hopefully 2 more quick things and we'll be done. So I mentioned before, here's just a trick for single digit multiplication of kind of big numbers. So let's say you're doing 7 times 8 and you're not quite sure what that is. Well, what is the complement of 7? 3. Complement of 2? 2. 8. Now, 10 minus 3 minus 2 is what? 5. 3 times 2? 6. And what's the answer here? 56. So, if sort of the big single-digit numbers are a little bit tricky, this is something you can do. You write them as their complements. You sum them, subtract from 10. That's the leading tens digit. And then you multiply them, and you get 6. Now, why is that true? Well, basically I'm viewing 7 as 10 minus 3 and 8 as 10 minus 2. So I'm just, no, sorry, yeah. So I've got that in my mind. And if I draw in my little box here, I like boxes sometimes. Got minus 2 and a minus 3. So 10 times 10, that'll be my 100. 10 times minus 2 is minus 20. 10 times minus 3 is minus 30. Minus 3 times minus 2 is plus 6. And so my answer is add all this up. So it's going to be 100 minus 20 minus 30 plus 6. So the 6 is the 3 times 2. That was this part. And the 20, 30, and 100 here, well, if I take out a 10, that's the distributive property, I'm left with 10 minus 2 minus 3, and that becomes the 5. 5 times 10 is 50. 50 plus 6. So that's why this method works. Basically get all those nice little rules, applying it in box formation. But it's a trick. So I can do another one just to do that. I'd write the 7 as a 3. I'd write the 9 as a 1. 3 plus 1 is 4. Subtract that from 10, I get 6. 3 times 1 is 3. 63. Alrighty. In general, as I said, you should just know these by heart, but in the lead up to that, if you don't know them, that trick may help. It works well when these numbers are really big. When they're kind of more moderate sized, like 5 times 6, it gets a little weird. So a complement of 5, complement of 6 is 4. 5 and 4 is 9. Subtract that from 10, you get 1. So that's kind of a 10. And 5 times 4 is 20. So it still works, but it's not actually any better. It's still like, still a lot of work. So it only kind of helps out with these larger single digits. Okay, I think that's enough for today. Next time, which will be next Wednesday, I will be here. I'll do division, and I'll also show you how to check the answers for stuff without having to redo things. Okay. Thank you.